Hi all, sorry, and welcome to now lecture 10 of CHY 113. Starting to really get into the thick of things this semester and get into our groove a little bit. And so let's go ahead and jump right into our warm-up questions. Remember last time we started to discuss the limiting reactants involved in stoichiometric problems as well as percent yield. And so let's take a look. And so in this first example, calculate how many grams of NH3 can form when 256 grams of N2 and 65.7 grams of H2 react. So remember all the steps that you will need to come up with this. First, your balanced chemical equation, then determine your limiting reactant, and then based on your limiting reactant, use that to figure out how many grams of your product could theoretically form. So go and pause the video now and see what you can come up with for an answer. Hopefully, you were able to come up with 311 grams of NH3. Let's go ahead and work through this one. And so, sorry, just let me organize myself a little bit here. Here we go. And so, as I mentioned, the first thing that we need to do is come up with our balanced chemical equation. And so we know that N2 and H2 are reacting. Sorry, my Apple Pencil's acting up here. I'll be back in just a moment. There we are, all fixed, and we are back. All right, so let's come up with our chemical equation then for this production of ammonia. So we have N2 plus H2 react to form NH3. And then we still need to balance our equation. 2NH3 to balance our N's, and then 3H2 to balance our H's. And so the first thing we need to do is to determine our limiting reactant. For this example, I'm going to go ahead and use the method of finding out the ratio of what we have versus what we need. And so we're going to start with our 256 grams of N2. We'll convert that over to moles using the molar mass. We see that we have 9.14 moles of N2. Then we're going to do the same for H2. We're starting with 65.7 grams of H2, divide by its molar mass, and we have 32.6 moles of H2. And so now we need to determine those basic ratios of what we have versus what we need. And so like I said, I normally take the larger one, just divide that by our smaller one. So I'm going to take my 32.6 moles of H2, divide that by 9.14 moles of N2, and I get a ratio of 3.56 moles of H2 per every 1 mole of N2. And so remember then that this is what I actually have. This is what I'm given in my experimental problem. Let's compare that now to what we need from our balanced chemical equation. We can see that what we need, and remember there's a 1 here. And so what we actually need, according to our equation, is 3 moles of H2 to every 1 mole of N2. Oop, N2, there we go. And so what we can see here then is that we have more than enough of the H2. For every 1 mole of N2, we need 3 moles of H2. We have 3.56 moles of H2. So we have more than enough H2 than what is required. This means that H2 is our excess reagent. There's more than enough of that than we actually need. And then N2 is what is actually going to limit our reaction. And so part of the reason that I chose this was also to demonstrate for you, like I mentioned in the last lecture, that you can't simply look to what you have more of or less of in your starting amounts. Yes, we have a lot more mass of N2, but our moles of N2 are what really matters. And then not only that, we also have to look at the balanced chemical formula, which will definitely come into play as well. And so now that we know that N2 limits our reaction, we're going to base our calculation off 9.14 moles of N2. And so we have 9.14 moles of N2 from our equation on the previous slide. We form 2 moles of NH3 per every 1 mole of N2. And then finally, we use our molar mass of NH3, 17.304 grams of NH3 per 1 mole of NH3 to give us a final number adjusted for significant figures of 311 grams of NH3. And that's our final answer. And so there are, like I mentioned in the last lecture, there are multiple methods of finding limiting reactant problems. You could have just done this whole problem out and calculated how many grams of NH3 form from 256 grams of N2, and then calculated how many grams of NH3 form from 65.7 grams of H2. Whichever one formed less would have been your limiting reactant and the amount. That would have been the 311 grams of NH3. You could also set up a before, change, and after table like we looked at and go about things that way. However you approach limiting reactant problems is entirely up to you. There are several methods of doing so. And so now, try a couple more. Ooh, sorry for that one. I just flat out gave you the answer right away. So let me pause and fix that one. I'll be right back. That's better. So in this problem, it's the same exact idea. We want to find out how many grams of silver chromate will precipitate when we're given a certain amount and molarity of silver nitrate and a certain amount and molarity of potassium chromate. And so in this problem, same as before, you want to come up with your balanced chemical equation first, and then determine your limiting reactant and base your problem off that. The only difference here is that instead of using mass and your molar mass to convert to moles, we're given our volume and our molarity. So you'll have to work through your pathway to find moles that way, but it's the same exact idea. And so go ahead and pause the video now and see what you can come up with. Hopefully you came up with 12.4 grams of silver chromate. Now, instead of doing this one out, I will just point you to where you can find the solution. Remember that there's lots of extra practice on the materials page of every unit. So if we go to Unit 2 materials, you'll find some extra practice and limiting reactants with the key. And so this is a problem that I took directly from there. Next one, same exact idea, only now we want to also calculate a percent yield. And so we're going to go through our theoretical yield the same way that you've done before, and then use the actual yield of 0.224 grams to calculate your percent yield. Pause the video now, see what you can do. So you should have calculated a theoretical yield of 0.427 grams. Again, go ahead and see that same worksheet for the solution to that and how I found that amount. And so then for the percent yield, we're simply going to take our 0.224 grams that we actually came up with, divide that by the 0.427 grams of theoretical yield, and multiply by 100 to convert to 52.5% yield. And those are our practice problems. And so let's go ahead and get into our next section of stoichiometry. In this section, what we're going to start to really look at is how we can really use some of these principles in other ways. How we're able to use these principles of stoichiometry in order to really do some good chemical analysis. We're going to look at two particular types, one called gravimetric analysis and another called the combustion analysis. So there's a certain mineral called thernodite, which contains some sodium sulfate as one of its primary, one of the primary chemicals that makes it up. What we want to do is we want a way to actually calculate the percentage of sodium sulfate that's in this material. So we want to be able to take this mineral here, this sample of thernodite, and see what percent by mass of that mineral is just the sodium sulfate. And so what we do first is we can dissolve the mineral, and then we can add some barium chloride to that. What the barium chloride is then going to do is react with the sodium sulfate that is in the thernodite, the sodium sulfate that's in the mineral. And so we have our sodium sulfate here and the barium chloride. We use our solubility rules, and we see that barium sulfate is going to come out as a precipitate from that. And so we can use that information. We can use that then. If we sort of look at this overall process here, we have our dissolved mineral here, which contains our sodium sulfate. We add some barium chloride to that, and we can see here that when that happens, when we mix the two of them together, we're going to form a precipitate. We have this white, cloudy sort of residue that forms in there to start out. We allow that to settle. We allow the solid, the precipitate to really form in there. And then we just filter it. We filter, and when we collect the solid barium sulfate on filter paper, we allow that to dry. And then we can find the mass of that solid barium sulfate. The key to this type of analysis, and this is called the gravimetric analysis, the key to this type of analysis, especially in this particular example, or sorry, we'll come back to that. So in this example, and we'll go through this, is we had a 0.123 gram sample of the mineral. From that, we actually recovered 0.177 grams of barium sulfate. And we're going to use that information to actually calculate the mass percent of sodium sulfate. And so the key to this is recognizing that all of the sulfate that was in the sodium sulfate is going to now end up as barium sulfate. The sodium sulfate is our limiting reactant. We add more than enough of the barium chloride. Barium chloride in this type of analysis would be far in excess. So we make sure that all of the sulfate that was in the sodium sulfate initially is going to now precipitate out as barium sulfate. And that's just the chemical reaction that we showed earlier. And again, we can see that all the sodium sulfate that was aqueous and all the sulfate especially is now coming out and precipitating out as barium sulfate. So all the sulfate that was originally present in our sample is now going to be locked up in this solid barium sulfate. And so what we can do then is we can simply take the mass of this barium sulfate, convert that over to moles. And so the number of moles of barium sulfate that I get in the end had to have been equal to the number of moles of sodium sulfate that we had to begin with. And so let's take a look at how we use that information. And so we can take the grams of barium sulfate that we end up with, what we actually end up with dried for barium sulfate on our filter paper. And just like any stoichiometry problem that we've done so far, we're going to take that and convert it to moles of the barium sulfate. We'll use our balanced chemical equation to then convert to moles of sodium sulfate, and then use the molar mass of sodium sulfate to convert to grams of sodium sulfate, which we can then use in conjunction with the total mass of the mineral that we had to find the mass percent in the mineral of the sodium sulfate. So let's take a look at doing that whole calculation out. And so we said, I think I don't want to go to the next slide quite yet. No, I don't. Okay. And so we had said that we formed 0.177 grams. Oh, sorry. 0.177 grams of barium sulfate. And so, like I mentioned, our first step is to just convert that over to moles of barium sulfate using the molar mass of 233.4 grams of barium sulfate per 1 mole of barium sulfate. Our balanced chemical equation told us that it was a 1-to-1 ratio, 1 mole of barium sulfate per 1 mole of sodium sulfate. And then the molar mass of sodium sulfate of 142.0 grams per mole. And we find that our initial sample then contained 0.108 grams of sodium sulfate. We take that 0.108 grams. So that was how much sodium sulfate had to have been in our initial mineral sample. Or that initial sample of thernodite had to contain 0.108 grams of sodium sulfate. So we take that 0.108 grams and divide that by the total mass of the mineral that we had to begin with, multiply by 100 to convert to a percent, and we see that the initial sample of thernodite contained 87.8% sodium sulfate. And so of any sample of thernodite, as long as we can assume that any sample is going to be pretty much the same, any sample of thernodite by mass will be 87.8% sodium sulfate. And that could be powerful information depending on what we're trying to do. And this slide is the same thing, just walks you through exactly what I just did. And so we have our first initial step, converting over to moles of barium sulfate, using our chemical equation to convert to moles of sodium sulfate, and then finally the molar mass of sodium sulfate to get to our 0.108 grams. And the 0.108 divided by 0.123 to eventually get to our mass percent of 87.8. And so that's a gravimetric analysis. The basics of gravimetric analysis are that we take something for a substance that we can dissolve, something for a substance that we can get into an aqueous form. We'll react that with something else in order to form an insoluble precipitate, which locks up one of the items that we're looking for. In this case, it was the sulfate. And so then we're able to then filter out and dry that precipitate and just do some simple stoichiometric analysis to find out how much of the original ion of interest, so to speak, was present in our original sample. The next type of analysis that we're going to talk about is called the combustion analysis. Now, remember way back when we talked about empirical formulas a few weeks ago, I had talked about how empirical formula is a powerful tool that we can use, because if we don't know the identity of a sample, if we have especially a sample of some sort of hydrocarbon, if we don't know what it actually is, we can send it through a combustion analysis and find the empirical formula of that unknown compound. And so that's what we're going to look at here, is how we can use stoichiometry in order to find the empirical formula of an unknown compound. And so specifically here with hydrocarbons. So hydrocarbons containing carbon, only carbon, hydrogen, or oxygen. So something like glucose, C6H12O6, is a hydrocarbon. When hydrocarbons burn in oxygen, when they go through a combustion reaction with oxygen, the only products, and these are the only products if it's a pure hydrocarbon, nothing else in there, the only products of that reaction are going to be H2O and CO2, just water and carbon dioxide. And if we have a combustion reaction set up, we can collect those. We can actually collect the water that comes off by using something called magnesium perchlorate. And so this would be just a little system set up to collect that water, where the carbon dioxide will then pass through. And then we can set up an apparatus which will collect the carbon dioxide. It's absorbed by sodium hydroxide on basically on an asbestos platform, so to speak. And so don't worry about that. I'm certainly not going to hold you responsible for knowing how we absorb the water and the CO2, but just know that we can. And so what we can do is we can burn our hydrocarbon in water. We can combust our hydrocarbon, sorry, not in water. We can combust our hydrocarbon in oxygen. And then we can collect the resulting H2O and CO2 and find the mass of those. And that's going to be the key part for us. And so let's demonstrate this with an example. And so in this example here, we have 1.516 grams of a generic hydrocarbon, contains only carbon, hydrogen, and oxygen. And we have our generic formula for that right here. So CXHYOZ. What we're going to do is actually find this X, Y, and Z. And so we're told that when we send this through our combustion analysis, we are able to collect 2.082 grams of CO2 and 1.705 grams of H2O. Using that information, we're going to be able to calculate the empirical formula of this compound. We also have a mass spectrometer on hand for this particular example. Using a mass spectrometer, we can find the molecular weight of any unknown compound. So we can find the molar mass, the molecular mass of this compound, and we find that to be 160.2. We're going to use that information combined with the empirical formula to find the actual complete molecular formula of this unknown compound. So let's see how we do this. And so the first thing that we're going to do is we're going to use our mass of the CO2 produced to relate that back to how much carbon had to have been present in the beginning, how many moles of carbon. Because it's important to note as well that in our, who knows where I hid my Apple Pencil? There it is. And so in our sort of generic equation, CX, so our generic hydrocarbon, CXHYOZ, it's going to react with O2, form CO2 and H2O. What we have to recognize is that the carbon in the CO2, the only place that could have come from, the only possible source of that carbon had to come from the carbon in our initial hydrocarbon. And so if we are able to find the moles of carbon in CO2, that had to have been equal to the moles of carbon in our unknown hydrocarbon. That's the only place that carbon could have come from, was from that unknown hydrocarbon. And so that's what we do. And so we take our 2.082 grams of carbon dioxide, we convert that over to moles of carbon dioxide, just using its molar mass. And then for every 1 mole of carbon dioxide, there was 1 mole of carbon present. And so now we know that there had to have been 0.04731 moles of carbon in our initial sample. We can do the same thing with hydrogen, because we also know that the only place the hydrogen in the water could have come from had to have been from the hydrogen in our hydrocarbon. And so we're going to take the mass of water, 1.705 grams of H2O. We'll convert that over to moles of H2O using its molar mass. But we're trying to find the number of actual moles of hydrogen. So now we do have to take into account that there are 2 moles of hydrogen in every 1 mole of water, just from the chemical formula here. And so doing that tells us that we had to have had 0.1892 moles of hydrogen in our initial hydrocarbon. So we're almost there. We now know how many moles of carbon had to have been initially present. We know how many moles of hydrogen had to have been initially present. Now we just need to find out how many moles of oxygen we had. And once we have all three of those, we can use those to find our empirical formula, just like we were doing a few weeks ago. The moles of oxygen isn't quite so straightforward, though, because we do run into a problem. First, oxygen is present in both the CO2 and the H2O. Oxygen could have also come from either the hydrocarbon or the oxygen that we used for combustion. And so we have to just go about finding the oxygen in a little bit different way. What we can do here, oh yeah, and sorry, don't forget that ratio. And so, and it's just talking about that same thing, that we don't necessarily know exactly where all the oxygen came from. We don't know how much it came from the hydrocarbon, how much from the O2 that was part of the combustion reaction. And so what we're going to do, what we have to recognize, is that the mass of the original sample contained only carbon, hydrogen, and oxygen. And so the mass of that sample minus the mass of carbon and minus the mass of hydrogen has to be equal to the mass of oxygen that was present. And so what we're doing here, this is our mass of our original sample, was 1.516 grams. This is the mass of our carbon and our hydrogen in that sample. And all we did to find those was we simply used the moles of carbon here and the moles of hydrogen here. So those are the moles of carbon and hydrogen that had to have been present in our initial sample. And we just converted those over to grams. And so our this is 0.04731 moles of carbon. So just using the molar mass to convert those over to grams now. Sorry, 0.1892 moles of hydrogen, its molar mass. And that is what then gets us to the mass of carbon and hydrogen that had to have initially been present. We subtract those from the original sample mass, and so we know that our original hydrocarbon had to have contained 0.757 grams of oxygen. And then we just use oxygen's molar mass to convert that over to moles of oxygen. Now we have the moles of all three of the constituent parts of our hydrocarbon. We know the moles of carbon, we know the moles of hydrogen, and we now know the moles of oxygen. And so just like we did before, we divide each of them by the lowest number. We did this when we were doing empirical formula problems in the first unit. So the lowest number is 0.0473, and carbon and oxygen are pretty much the same. So we're going to divide each of these by 0.0473, and that gets us, that division gets us what the values are for each. And so for carbon, 0.0473 divided by 0.0473 gives us 1. So there's our subscript for carbon. 0.1892 moles of hydrogen divided by 0.0473 gives us our subscript of 4 for hydrogen. And then for oxygen, 0.0473 divided by 0.0473 gives us our subscript of 1 for oxygen. And so the empirical formula for this unknown hydrocarbon is CH4O. Now we also had some information about the actual molecular mass in order to find the entire molecular formula. And so if I remember right, we did do this as well in the first unit, but the basic process here is that what you want to do, and then this is a fairly complicated slide, but just know that the basics of it is you want to take the molar mass of the entire compound that you were given. So in this case, we were told, we go all the way back here, The molar mass of the whole compound was 160.2. So we're going to take that 160.2 and we're going to divide that by the molar mass of our empirical formula. And so in this case, we were given an empirical formula, or we found an empirical formula of CH4O. And so the molecular mass of this that's a 4 there. And so the molar mass from our empirical formula is 32.041. And so we're going to take I forgot it again already. What was it? 160? 160.2. So we take 160.2 divided by 32.041. .041 gives us 4.9998. Basically gives us 5. That 5 now is the scale factor that we use with our original empirical formula. We just scale everything up by a factor of 5, giving us a final molecular formula of C5H20O5 of this unknown hydrocarbon. And that's, I think, all I have on the next slide. There it is. Oops. So what we've done here, and you can hopefully you're starting to see where this is a powerful type of analysis. What we're able to do is if we have this completely unknown compound, we have no idea what this compound is. We have this mysterious white powder that somebody brings into the lab, and we want to know what it is. We can send that mysterious white powder through a couple different analyses. One of those is simply a mass spectrometer, which is something that we're not going to get into in here, but know that a mass spectrometer will enable us to find the molecular weight of the compound. We can then also send this mysterious white powder through a combustion analysis to find its empirical formula. The two of those combined allow us to then find the molecular formula of this completely unknown thing. That is a powerful analysis. That is a powerful thing to do, is to be able to combine these types of analysis and find the molecular formula of a completely unknown compound. And what we're doing, all that we're doing for it in order to do this, is once we have the data, we're using simple stoichiometric principles in order to find that. I think that's pretty powerful stuff, personally. And so that is all for today's lecture. The next couple lectures are going to be a little bit shorter than usual, because there's not a lot to present as far as the actual process and what we're doing. The work now is going to come from you guys doing a lot of practice problems associated with these. I don't expect you to fully understand everything that we just worked through. You need to do a lot of practice problems in order to let it sink in. And so spend some time working with this. Again, if we go to our Unit 2 materials page here, extra practice. Oh, and I thought I had, maybe I don't. I thought I had some practice with some combustion. So I don't have practice with combustion analyses on this page here, but I do have some other examples I think that I go through in the supplemental videos, and so that will help you out. The other thing that I have done is if you go into Chem 101, there should be some practice problems available to you there now. So we go over to our practice tab, Unit 2 practice, and there's some general stoichiometry, some stoichiometry limiting reactants. Those were both of last week's lectures. But then also some stoichiometric chemical analysis. And I don't know why it's not actually letting me. Well, something's glitching with mine right now, but if you go into this, you can definitely work those practice problems. And so there are some practice problems associated with combustion analysis right in Chem 101. So do a bunch of practice, watch that supplemental video, and watch me do a couple more practice problems, and you'll get the idea. And so that's all for today. We do have one more lecture with stoichiometry involving some specific solution stoichiometry and a type of analysis called titrations. But then that will be it for stoichiometry. And after that, we'll move on to thermochemistry. And so that is all for today. I hope everybody has a great day.